Welcome to Statistics in Excel number 76. Hey, if you want to download this workbook and follow along, click on my YouTube channel, then click on my college website link, and you can download the workbook Business 210 Chapter 7. If you're in the class, just go to our Chapter 7 website. Hey, we got to talk about the sampling distribution of X bar. This is going to bring us real power because we'll be able to take a sample and have some way of seeing whether our sample is reasonable or not. And that matters because in the real world, when we're analyzing data, a lot of times we don't have population data or information. So we need to base our decisions on samples. Now let's remind ourselves what we did in Chapter 6 and what we're going to do in Chapter 7. Chapter 6, when we had mu equals 12, population mu, standard deviation of the population equals 2. We took an x value and compared it. We either said less than or equal to, greater than or equal to, or between. What was the probability that we could get a particular x below this 10, for example? We also saw how to convert to z and use the standard normal curve. But x is not what we want. We want to start talking about x bar. So here's what we're going to do in this chapter. We're going to plot x bar. And we need to have some sort of normal or standard normal curve that we can use to make probabilistic statements. Find out whether our sample mean is reasonable or not. So we got to figure out how we can get away with plotting x bar on a continuous probability distribution. Now let's do some investigating first before we get into all the formulas and how to do calculations. Let's go over to the sheet called Sampling Distribution of X bar. I actually want to construct a sampling distribution of sample mean. If you have a really small data set, we can do it. And that's what we're going to do just to gain some insight and see that it is legitimate to take a sample, get an X bar, and compare it to a standard normal curve. Because really, that's what we want to do in this chapter. Now, here's a law firm. Here are some partners. They've reported their hours. So this is going to be our population. So I would like to do first count how many partners we have. Count. And I'm going to use count because I'm counting numbers. If I was counting names, I would use equals count because count counts words. Actually, count counts cells that are not blank. All right, so the total population size is fine. That's our big N. Our sample size is going to be little n. Well, what would we do to go about to calculate all the possible samples we could extract from this population? Because here's the deal. One of the tricks for us, we're going to try and prove that population mu equals mu sub x bar, or expected value of x bar, which means if we plotted all of the x bars, we would have some expected value, or mu. And we're going to prove that these are the same. What we need to do is take all the possible samples of sample size 2 here. The way we do that is using combinations, the combin function. We've seen this a few times so far in this class. So we're going to say equals combin. The number chosen, the total number in the population is n, comma, and the number chosen is 2. All right, so 10 samples. That's the total possible number of all sample sizes of 2. Now, we want to actually list those, and then that will give us all of our sample means. Because remember, what are we talking about? We're talking about plotting all of the sample means, or x bars. So we want to get an idea of what that distribution would look like. So how do we calculate all those? Well, we got to figure out what all the samples are too. Now, we've done this a few times in this class already, when we listed all of our sample points or our experimental outcomes in a sample space. So what we need to do is think. Dunn can be matched with Hardy. Dunn can be matched with Kears. Dunn can be matched with Mallory, etc. Now watch this. I'm going to copy Dunn, and I'm going to come down here and I'm going to highlight 4 cells. Because notice Dunn can be matched up with 4 people. So I'm going to highlight 4 cells and Control V. That'll put Dunn into each one. Now let's go up here. Oh, Dunn has to be matched up with all these, so I'm going to highlight that and copy and paste that right there. Now let's go to the next person. Hardy. OK, we need Hardy and Dunn. Oh, no, that would be what we're calculating a permutation. We're not. We're calculating a combination. Remember, that combination formula tells us all the possible samples of size n from a population of size big N. Right? So we can skip Hardy and Dunn. So I'm going to copy Hardy, and notice there's 3 people left. So I highlight 3 cells and Control V. Now I highlight these 3 people, because those are the 3 people that Hardy needs to be matched up with. Copy and paste. Control V. Now let's go up to the next person. Kears. Oh, there's 2 people left, so we'll copy Kears. Control C. Highlight 2 cells and Control V. Oops. Highlight Kears. Copy. Control C. Highlight these 2 cells and Control V. Now we can go get the 2 people that Kears needs to be matched up with. Copy. Come down here and Control V. Finally, there's only 1 person left. Now watch this. Here's a cool trick. Mallory needs to be matched up with Tillman. If you highlight both and copy, you know if you pasted right here, it would go this, here, and here, right? But watch this. Right-click Paste Special. And there's a transpose. This is Paste Special Transpose. And it will take something that was orientated like this and paste it like this. All right, so we have all of the possible combinations. Now, 2 videos ago, or both of the last 2 videos, we used the VLOOKUP function. Now, I just want you to point out something. Notice VLOOKUP is perfect. If I wanted to look up the hours for Dunn, right? I'd take Dunn into my head. I'd come over here. I'd race through the first column. Oh, I'd find that one right there. I'd jump over to the second column. I'd take that 22 and put it right there. So instead of doing this by hand back and forth, you can do the whole thing all at once. Highlight all of the cells, and in the active cell, I'm going to use VLOOKUP. Equals VLOOKUP. What is the lookup value? Now, it's done for this cell, but what about when I copy it over here? Do I want it to move to Hardy? Yeah, because I need to calculate an average here, the mean. So I need to list all of the possible hours from that population over there. So watch this. As I copy down VLOOKUP, in this cell, it's going to be looking to Hardy. When it copies over here, it'll be looking to Mallory. So that is a relative cell reference. Comma. Now, the table. The lookup table, just as we said, when you're doing it by hand, you know where the table is, but VLOOKUP doesn't. So you have to highlight the table and say, hey, VLOOKUP, that's where that table is. Now be sure and hit the F4 key there, because it needs to be locked in all directions. Now, comma, column index. Remember, the way you do it is you race down here, you find the person you want, you jump over to this column, take that 30 and bring it back over there. But VLOOKUP doesn't know that. It needs to know which column to take the thing from. If we put a 1, it would just bring Kears over, which wouldn't do nothing here. We want to tell it 2 because it's in the second column. So I'm going to put a 2. Now remember, this is the 3rd time we've done this, and every single time it's been a column in A, B. But this table could be anywhere. It does not have to be in column A and B. Now, comma, and the final argument is approximate or exact. We're looking up a name. We want to find exactly done, so we're going to put false for exact match or 0. Now, close parenthesis, and you're not going to believe this. Control Enter. And did it work? Well, first, let's edit over here and hit F2. OK, it got that name right, and it looks like it's locked there. But let's just do a little trick. Kears and Tillman, 30 and 22. Kears, 30. Tillman 22. That is just amazing. Now, when you're learning Excel and VLOOKUP, it's confusing and it may take a while to do it. But once you get the hang of it, imagine your boss saying, please, do something like this. And you coming over and highlighting all the cells and creating a formula and Control Enter. And there, it's done in, a minute or so. When you're learning it, it takes 5 minutes to figure out. All right, now, how do we calculate all of the possible means, all of the sample means for every single one of our samples? You highlight all the cells and type average. These are going to be relative cell reference, just like that. Control Enter. There's all of the sample means. Now, I want you to notice something, and this is going to be very important. Remember, we're trying to figure out what in the world this sampling distribution of x bar is. This is a sampling. It's called, that's the phrase they call it. It's really all the x bars plotted, right? But they call it a sampling distribution of x bar. Now, we want to notice something. Notice this, it goes from like minus 3 standard deviations to 3 standard deviations, goes from like 13 to 11, right? Look at the x's. This is the data we used from last chapter. The x's for 3 standard deviations goes like from 5 to like 19, right? How come the range here is much bigger on a distribution of x's, and then when you get over to x bars, it's like really small? Why is it? Hey, look right here. These are averages, right? 24, 26, 24, 22, 28, 26. So the range here is like from 24 to 28, like a range of 4. But look at over here. We have some 30s, some 22s. Of course, that makes perfect sense. The variation in a distribution of x bars is always going to be much smaller because we're plotting averages. Anytime you take an average, it is the one in the middle. It's the typical value. So when you plot all of the sample means, you're going to get a much tighter, narrower, not as much dispersion, not as much variation distribution. So, and we can see that here with our eyes because these are all clustered together where the actual sample data is much more spread out. Now, our goal is to see that mu sub x bar, which just means what's the average of all of the possible samples. We want to prove that it's equal to the population mean. So we'll do equals average. Now, what are we doing here? We're doing an average of all of the averages. 25.2. All right, now let's calculate our average for the population. Let's come over here, highlight all of that right there. All right, and then enter. What? They're the same. You better believe it. If you can take every single possible sample of size n, whatever it may be, and calculate all the means, and then calculate the mean of all the means, you are always going to get that equal to the population mean. And do you see what that implies? That means that when we start plotting our distribution here for sample means, this right here down the middle is going to be the exact x bar mu or mean or average, and it's going to be the population. So when we're actually taking x bars and trying to compare them to the population, we'd be able to say things like, we believe that the sample mean will be within 68% or 1 standard deviation on either side from the population mean. So that's very convenient that this is true. In this textbook, they use expected value of x bar. In other ones, they just say mu sub x bar. But these two will always be equal. So if we're able to select all possible samples of a particular size from a given population, then the mean of the sampling distribution of sample means will be exactly equal to population mean. And if we can't take all of the possible samples, these two will be approximately equal. Now, that's conclusion number 1. Let's look at something else. I want to actually do the distribution, a frequency distribution for the population and for the sample means. Now, I've already set this up, but let's go ahead and look up here at the population data. So we have a 22, 22. So it looks like there's some 22s, some 20s. So there's 3 values. So how do we count how many of each there are? Count if. I'm going to highlight all the cells and equals count if. I'm going to go up and count the range. Zoop. And I'm going to hit F4. Not only does it lock it, but it jumps the screen back in view, comma. And what are we counting? A relative cell reference right there. All right, so there's a 2, 2, and 1. Notice we did distribution. Now, we have a very small data set here, so we can, if we had a huge data set, it would take us an hour to do this video, and it would be ridiculous. But even with this small data set, we can gain some real insight into how the sampling distribution of x bar looks. Okay, so that's how it looks. It looks pretty skewed this way. Now, let's do a distribution of the sample means, right? We already know that they should be clustered more together, right, because they're all averages. Let's highlight all of these, and in the light colored cell at the top, I'm going to type equals COUNTIF. I'm going to go get the range over here. And I'm going to hit F4, comma, that one right there, close parentheses, and Control Enter. Aha, so a 1, a 4, 3, and a 2. You can already see what happens. It starts to get much more bell-shaped or normally distributed. So conclusion number 2, and this is going to lead us to the central limit theorem. Let me change the size here. If all samples of particular size are selected from any population, the sampling distribution of the sample mean, so that's what they call it, sampling distribution of sample mean, which is what we just did, x bar is approximately normally distributed. This approximation improves with larger samples. Now let's go over and take a look here. This is a picture from a textbook, right? Here's, oh, look, that's like for skateboarders, a half pipe. Here's another quarter pipe for skateboarders, and there's a jump ramp for skateboarders. But, oh yeah, this is like the exponential. This is the uniform. Here are some other distributions when you plot them. This is what they look like. Well, look what happens when you do sample size 2. They already start to look more normal. No way. N equals 6? 6 isn't even that very big. Look what happens when you get up to N30. You got to be kidding me. So as N increases for our x bar, notice that's x bar, x bar, x bar. This is the plot of the x bars, which is what we've been doing in this video, sample distribution of x bar. As soon as you get up to around 30, it's like, doesn't matter what you started with, the distribution will be bell-shaped. What does that mean? That means we can use the standard normal curve. Get this. We take one sample, and because we know the distribution of sample means is normally distributed, if our sample has a big enough n, we can just take our sample, do a couple calculations, and compare it against the normal standard curve. Very powerful stuff. Now let's go over here and look at the central limit theorem. It's just this set a little bit different. In selecting simple random samples of size n from a population, the sample distribution of the sample mean can be approximated by the normal distribution as the sample size becomes larger. This is just formalizing what we just said, right? We can take an x bar and just use the normal distribution. Now, here's kind of the rule 10 if the original distribution is sort of symmetrical. Even thick-tailed distributions when n is greater than 30. Even heavily skewed or distributions with huge outliers, when you get up above n equals 50, they converge on the normal. Now, what is, and by the way, our x bar is going to be our random variable now. Now, uses. This means that we can reason about the sample distribution of x bar with absolutely no information about the shape of the original distribution from which the sample is taken. This means that we can take one sample and compare it to the standard normal curve using norm S dist, that's the standard, or the normal curve, norm dist. You know, in the old days before Excel, you always wanted to use this one because you could just use one. But now with this one, you could use either one, and this is just as easy. To see if our sample results are reasonable or not. So we're going to be taking our sample, comparing it against the standard normal curve, and saying, hey, does it seem reasonable? For example, if the filling machine for a cereal box, we know that the box says 14 ounces. So that machine should be filling 14 ounces. Well, now, with the central limit theorem and norm S dist and norm dist, we can take a sample. And if we get 14.4 ounces from our sample, we will learn how to compare it to the standard normal curve and conclude whether the machine is filling accurately or it's not. Obviously, if it's not, then you close down the machine and fix it. And guess what? They do that kind of stuff all the time in filling companies or manufacturing companies. So if it's reasonable, meaning our mean, the process, like filling, or the claim, like something on a box, is reasonable. If it's not reasonable, the process or claim is not reasonable. So we're going to see how to do this. One last important thing before we see a great example. Standard deviation. Oh, wait a second. We already talked about this, right? Much smaller. The variation in dispersion is much smaller because what? You're plotting averages. So here's the formula. We're in this chapter going to know the population standard deviation sigma. Next chapter we'll see what we do when we don't have sigma. But you can't just use sigma. So let's go back over here, right? You can't just use standard deviation equals 2. Actually, I had it plotted here. If the population standard deviation is 2, which in this chapter we'll know, next chapter we'll see how to do it without it, then we'll figure out how to calculate the sampling distribution x bar standard deviation. Because if we're plotting x bars, we need a standard deviation, right, to say 1 standard deviation, 2 standard deviations. This is what it will turn out to be, and it's just the formula is whatever your population standard deviation divided by the square root of n, and that will give us our what's called standard deviation of x bar, or it's called the standard error. Now here's the official formula: square root of big N minus little n divided by big N minus 1, square root of all that times sigma divided by the square root of n. Now here's the rule. This thing is called a correction factor, and we'll get it when we do proportions too. Correction factor. Basically, the textbook assumes that all the problems don't need this correction factor. But it's easy to tell. You just take n divided by big N. If it's less than or equal to 0.5, then you do not have to use this. Now here's the deal. Think about it. If you do a sample in the United States, there's 300 million people, right? If your sample size is 400 for a political poll, 400 divided by 300 million is going to be tiny. So most samples, most populations are really big. Most samples are pretty small. And so this is a lot of the times the case. So you don't need this. So really, here's the formula. There's a great homework problem where you'll have to use this, and you'll learn something about that. But here it is. There's our formula. Now, and the reason why, like I just said, because populations are usually very big and samples are usually small, so the correction factor, we don't need it. Now, one other thing, the relationship between sample size and the sampling distribution of x bar. Oh, if we're calculating our standard error or our standard deviation of the sampling distribution of x bar here, it's going to be standard deviation divided by the square root of n. Well, what if n gets really big, right? 4 divided by the square root of 16, the square root of 16 is 4, is 1. Square root of 64 is 8, so 4 divided by 8 is 5. Just look at what happens to our distribution. And later in one of these videos, I'll give you a probability example of this. As n becomes big, the spread in the sampling distribution of x bar gets really small. Be sure you read this a few times, because this is the implication. The bigger the n, which makes sense, you want to get more samples because then it will be more representative of the population. But the bigger the n, the higher the probability that the sample mean falls within a specific distance of the population mean. All right, that's sampling distribution of x bar. When we come back in our next video, we actually get to see everything we learned in this video, the sampling distribution of the x bar. We'll use the x bar, the standard deviation, or the standard error, and we'll do some calculations to see if things are reasonable or not. All right, we'll see you next video.